DJ, can you move a little bit more to here?
Uh-huh.
Like right away. Let me see. Hi, everybody. We are here at the Robotic Learning Center. Today is our second podcast of Futuristic Friday. Today, we're going to talk about the physics and the relationship between physics and robotics and what is the future ahead of us. I am Mrs. G, Mrs. Gabaldon, the founder of Eco Robotic.
And I'm DJ Pacheco, your co-host.
Mm-hmm. And then we have a guest speaker.
So I'm Vladimir Mujica. I'm a professor at Arizona State University. I'm pleased to be here with DJ and Gabriela.
So let's get started. So let's start with what is physics? What can you tell us, Dr. Mujica, in your own words? What do you think is physics? What is physics actually?
Well, that might sound like a simple question, but it's not. Because if you want to enter into any detailed description, it will take us a while. But let's say that physics is the science behind the motion, microscopic motion, macro and micro, this is from planets down to electrons and nuclei. So it's the science behind interaction behind particles, light, electromagnetic forces, magnetic fields, etc. So all that goes onto that umbrella of physics. So it's if you want to put it that way, physics is the fundamental science, and then from there you get chemistry, biology. In a way, these are like big applications of physics.
So so now that you say that you go and you went far and beyond just instead, just motion. So what do you think, that it's so important, think about physics and robotics, which is like, robotics is no its own field, but can you tell us?
Yeah, so probably we can start. I don't know how much your students, robotic and people around here knows about the origin of the word robot. Robot, it comes, the original word is robota. It comes from the Czech language. And it was used to refer to forced labor. So in a way, it was a way of referring to people working on their, like slaves. So from there, it evolved into this word robot, and it was.
So that was a play, correct?
Yes,
that was a play.
But the word, the actual origin is robota.
Robota. So that right. I heard that before, and they actually will teach that.
Right. And then from there, you get robotics. Robotics is a discipline of engineering. And then robotics, it has to do with designing these machines that initially were supposed to carry over human activities in an independent way. And that was the original conception, but now it has become much more complicated than that. Because now robotics includes artificial intelligence, it includes computing, it includes the whole thing about electromagnetism. So everything behind robotics, the discipline, the engineering discipline, and robots, the actual machines, is related to physics. Because without that, we don't understand anything about how to design, build, operate robots.
So basically, we can say you don't know physics, you cannot be an expert on robotics.
No, if you want to study robotics as a discipline, you need to know a lot of physics, and at least the part having to do with circuits, how electricity goes through matter, magnetic fields, communication, data management. And now it is artificial intelligence too, and everything having to do with computer science.
Wow, this is, oh my gosh. I said, like, it's so, every time I speak with you, it's like You are so rich of knowledge. And then I speak. Do you have any questions for Dr. Mojica, DJ?
Well, not at this moment, but
Okay, but so let's think about what we're teaching here in class and go to the very basics: motion, kinematics, Newton. So let's remember, you're listening. The first law of Newton: an object in motion stay in motion, and an object at rest stay at rest, unless an outside force changes that. Basically, inertia. So starting from the very basic, what do you think is important that start that basic law number one with robotics, Dr. Mojica?
Well, as far as we think of robots as machines, then everything having to do with motion, speed, um, how how they perform work, because work in the basic definition is that you have a force that operates during a certain distance, and then you take the product of this work times the distance, and they give you the force, the work. So when you want to compute how much power you get from a robot activity, how much work you get, so what is the equivalent of work that you can get from a robot, etc., it is physics. Now, the whole of physics, of course, it goes to classical physics, what's called uh, dynamics, but the classical physics is the essentially the Newton's equation of motion, of course, and then you just enunciated two of them, that a body moving or at rest keeps doing the same thing unless a force, and but then the very deep in creation of Newton was that he was able to relate the force acting on a body with its acceleration. So he discovered that you multiply the mass of the body times the acceleration, which mathematically is how the velocity changes with time, then the force is equal to the mass times the acceleration. And that changed completely science, because from there, Newton, for instance, was able to explain the motion of the moon, the motion of the planets, and answer this basic question. So we have the moon orbiting around the Earth. So what keeps the moon doing that? So how come that the moon doesn't fall into the Earth?
Yeah, we would remember we were talking about
Yeah.
centripetal motion.
forces, yes.
Remember the activity? Can you mention? Do you remember the activity that we did with the water?
Oh yeah, that's right. We were spinning it around 360 degrees, and the water would not fall out.
So, like, give us a little explanation why.
Well, right. I mean, because that's essentially the same. I mean, the same balance between centripetal and centrifugal forces. One of them attracts, and the other goes in the other direction. And if you have them on the balance, then bodies they follow an orbit, and then you can actually prove that and apply that to either water, skating, practicing skating, everything that has to do with motion can be translated into this language. Then, of course, you have some other considerations, because together with the concept of force, a critical.
And which is the second law of Newton.
Yeah, right. In addition to that, you need the concept of energy.
Okay.
And once you have the concept of energy, then you have the whole of thermodynamics. The whole of thermodynamics has to do with the balance of energy that come from work and come from heat. Now, heat, in principle, everything you can describe using Newton's equation at the classical level. But then if you want to understand heat, you need to understand friction. It's not just that the energy is preserved, but you have to distinguish between heat and work as a way of transferring energy, and all this goes into robotics.
And everything connects us.
The moment that you have a circuit that generates heat, you have to take that into account.
Yeah, totally. Like, for example, if you want to pass me the blue robots, so a lot of this robotics, we don't have understanding the physics behind. A lot of us lost the energy being put into friction. There's a lot of friction. Even when you fill up your tank, a lot of your gasoline lost because the car, loses due to friction. And the more you increase efficiency and understanding those concepts of physics behind. But do you have, can you mention, we talk about the third law of Newton?
Yeah.
Um, so the action and reaction. So can you tell us a little bit about action? The third law of Newton, every force have an equal and opposite reaction. So thinking about, robotics and why it's so important, any thoughts?
Yeah, but again, once you enter into heat dissipation, which is something that you have here, now you have to go beyond this simple action and reaction, because that goes for mechanical forces. And probably the simplest example, if you are trying to understand pressure, pressure is originated by the collision, let's say, of gas molecules
Just think about all the particles right now, air
Yeah.
here, all colliding. Yes.
colliding against the wall, and then when it collides against the wall, it transfers momentum to the wall and the momentum back. This is the action and reaction principle operating there. The same if you collide with somebody, or a dog jumps and you, or
You got a new dog. So today, dog training.
So you will have action and reaction there too. And if you collide against the tree doesn't move, so then you take all the energy there. It's better off if you're going to collide against a tree that the tree falls, because then it carries some of the momentum of the energy. Okay, but once we enter into this domain, now we have to take about something that Newton didn't work at all on that, which is Maxwell equations. Maxwell equations, they're also revolutionized physics. And now Maxwell equations, they have to do with light, electric fields, and magnetic fields. And this is absolutely essential to understand how the thing,
especially with AI and all the, like
Yeah.
how the new quantum computer, all
Yes.
these computers that are, like
that was
machine learning,
another revolution of physics. I mean, you had the first important revolution, Newton's laws, then the second one, Maxwell equations for light, everything having to do with light and the way electricity and magnetic fields propagate or interact with matter. And then third revolution had to do with quantum mechanics. So quantum mechanics, I mean, the same way you talk about Newtonian mechanics to describe classical objects. Now, when you go into quantum mechanics, this is the mechanics of atoms and molecules and electrons. And this is another dimension of physics. And if you are trying to describe, for instance, why atoms are stable, let's say the simplest atom, the hydrogen atom, just one proton and one electron. The stability of that atom, simplest one, is impossible to understand without quantum mechanics.
Yeah, I remember, by the way, for the people that doesn't know, he was my professor of physical chemistry back in ASU. And I remember
Yesterday, right?
Yeah, that was a few years ago. That was before me start teaching. I would say it could be 16 years ago. It could be something like that. So one of the classes I was taking with him, it was like the understanding the hydrogen atom. Okay, so all the physics, bringing that classic physics that was so important, as a lot of people did that. You had to understand that classical physics. So DJ, you are like with your jaws drop. You're like, oh my gosh, this is like a high level physics. And I was telling you, like, we're gonna bring a professor. Yes, we did.
Yeah.
So any question, any silly question can come into
Even non-silly questions are allowed.
like he like pizza.
Right.
Any question, his favorite color, anything that you want to ask to Dr. Mojica, or even how he got to be a professor and be so,
Well, I actually do have a question.
Yes.
So, how can you use quantum mechanics in? No, I mean, can you use quantum mechanics for everything in space?
In principle, you can apply you can use quantum mechanics to describe the behavior of matter under any condition. Okay, in principle. But there are some there, there are some constraints and there is some limiting behavior. When you go into macroscopic bodies, let's say you or a baseball ball or whatever, quantum mechanics, there is a transition, there is a limiting case. You can actually show that under some conditions, for the laws of quantum physics become the laws of classical physics under some conditions. Okay, so then in principle you can use quantum mechanics for whatever. Now the point is, quantum effects, are you going to experience them in our daily life? The answer is yes. For instance, now you are looking at me. Vision is a quantum phenomenon. Vision implies that photons enter your eye and excite molecules right behind your retina. And then this excitation provokes these molecules to absorb the photons and get excited. And then there is an electric signal back to your brain. And this is what your brain processes as vision. And this is all quantum. If you want to go in another direction, mutations. Mutation is the first step in evolution, molecular evolution. But it's also the first step in cancer, because a mutation is the first event that changes the genetic response of a cell. Whether that genetic response is stable or not, that it depends on many things. But so quantum mechanics is it's in there in understanding all the behavior, magnetic behavior. For instance, I don't know whether you know this, birds. Mm-hmm. Birds, when they fly in flocks, they read the Earth's magnetic field, and this is how they orient some birds, how they orient when they are flying.
This is why they don't collide. They know when. This is what people are not 100% sure.
It is also related to that, but it's primarily related to reading the magnetic field. Oh. Now, to read the magnetic field is a quantum process. You can't not read the magnetic field with a classical process coming from it. So quantum mechanics is everywhere. But once we are describing, let's say, the motion of this or a ball or something, then it is enough with Newton mechanics, because it's a large object. You could try with quantum, but then it becomes impossible, because anything has 10 to the 23 particles, atoms, at least 10 to the 23. So if you want to use quantum mechanics in full detail, you will need to solve equations for 10 to the 23 particles, which you cannot.
Yeah.
So there is this whole process of how to make approximations going from quantum to classical to. So the answer to your question is yes, but if you can go in the limited direction of classical mechanics, you do that.
Well, actually, I have one last question. How can you get introduced into quantum mechanics at a young age?
Oh, that's a great question, by the way.
Yeah, that's a very good question.
But how we attract so many people to go to that field? Because there's not many people going to that field.
So the whole question of introducing young people, students to quantum, this is a very important question, and it's a difficult one. Mm-hmm. You have to be, you need to be very pedagogical, and then you need to find ways in which the basic ideas are immediately introduced. For instance, the basic idea of quantum mechanics is that, imagine that I am, let's use that nasty example. I am shooting with a gun. Now, you know that bullets, if you just, let's say bullets are going that way, and then you hide here, you know that you're not going to be hit by a bullet. No. But if the bullet is a quantum object, then it propagates, the bullet propagates like a wave.
Going different, like a atomic bomb,
and so it is going to hit you. So if we start thinking about quantum phenomena, then you might introduce the basic concept without having to do with the mathematics, because the mathematical quantum mechanics is not trivial. Basic is not super difficult, but if you don't want to go that way. So you need to introduce some quantum ideas. And for instance, quantum computing and quantum information, you have some beautiful examples there. At the moment that you understand that a regular computer works storing data in a sequence of binary sequence 0 1 0 1 0 1, then you get information. And then you understand that if you use quantum mechanics, you can store information in a huge amount of information, because then you don't have 0 1 0 1, but you have a continuum distribution of numbers. So but you know that between 0 and 1, you have infinite numbers. Between one half and one third, you have infinite numbers too, because you have all the fractional numbers. So quantum mechanics operates looking at the whole continuum of real numbers and complex numbers. So you introduce some of these ideas and then you compare to what you will get in classical physics. That could be a nice way to, to get young people interested.
Yeah.
But it's an open question. It's something
That's a very good question. Yeah.
That we, physics or chemistry instructors or professors or whatever, it's an important thing. How do you get young people interested in quantum? Yes.
No, that was a good question, DJ. And then, so I think it's it for today. I think having a great. I don't know if you want to add something else for the viewers.
Well, I actually do have one last question. Actually.
Yes.
You have to use a lot of complex math in quantum mechanics.
You do. The mathematics of quantum mechanics is complex, and then you need to know differential geometry, differential equations, integrals, Fourier transforms. I'm just giving you a list of things that you need. But once you have it in place, it's a beautiful math, because it's very logical. But of course, you need to pay an initial price. If you want to appreciate the beauty of it, you cannot just go there blind and say, oh, this is how beautiful. No, you need to. But yes, and I didn't mention it, but conventional quantum mechanics does not include relativistic effects. If you want to go trying to put together Einstein relativity with quantum mechanics, then you have something called quantum electrodynamics.
Wow.
And that is a lot more complicated, but then you have things like what she mentioned. You can explain the hydrogen. To explain, let's say, an atomic explosion, you need to understand that when you have an atomic explosion, you have particles that are fully transforming energy. So the particles are annihilated, and then they become energy. To understand this process, you need also relativity and quantum mechanics.
Wow. So I'm guessing a lot of people in our history had to use quantum mechanics.
Oh, well, quantum mechanics, the first time the concept of quantum was used was in 1900 at a meeting of the Physical Society in Berlin. It was Planck who used for the first time. Yes. So people started to, but then Einstein in 1905 came with 07. He came with an explanation of an experiment that's called the photoelectric effect. That's also used that. But the modern version of quantum mechanics was created because this is not discovered. This is something that people have to create with their minds. So it was created in 1926 by Schrödinger. And then a few years later, there was the first relativistic version, and that was Dirac equation. So you have Schrödinger equation, Dirac equation, and then you have many other physicists who have contributed to this. Yes.
Wow, this is a great conversation. So any few things that you want to say, DJ, the things that you like from this conversation, like 2 or 3 things, and then you say 2 or 3 things, and say 2 or 3 things, and then we're here for today. So go ahead.
I liked like something that I learned.
Yeah.
About like how quantum mechanics can, how we can use it in real life, right? And how we can use it in space as well.
Mhm.
No.
Mhm.
Your turn or my turn?
Well, my turn because you are the special guest here, and then you're gonna close the Futuristic Friday. So, well, I like is the history that Dr. Mujica brings. So, from 1900, talking about Planck and the importance of math, physics, and chemistry, how all combined to have the technology we have today. There can be technology today we don't understand well. The physics and then the computers that we have today. Thanks to the quantum. So I do have a question. Sorry, I brought it to before we start. Oh my gosh, I do have a question. So you have this NVIDIA computer, correct? So with this new quantum computer, can you explain a little bit of? Are you aware or a little bit more of that computer to be able to go so fast that you have ChatGPT, but you have other machine, other AI, such as those computers being created by NVIDIA?
Well, I mean, the basic thing about quantum computing is that you have the possibility of using quantum mechanics to perform all the things that you will do with a conventional computer. But then the difference is, as I mentioned, that with quantum computers, you have the possibility of carrying on zillions of operations more than with a conventional computer. And then there is also a question that is that will take us some more time to explore. It's called quantum entanglement. That you have the possibility of connecting bodies in a way that has nothing to do with Newton's equation. It's a quantum phenomenon. It means that two systems interact here, and they keep memory of this interaction regardless of the distance.
So that is the basic of machine learning, what they got the
Machine
physics
learning-
Nobel Prize,
machine
the
lear-
physics
machine
Nobel
lear-
Prize, or
yeah,
no?
Machine learning is a connected thing, but it's not entirely the same. Because in machine learning, what you do, let's say you have a particular process that you want to study. Let's say a chemical reaction that is important for pharmaceutical effects, pharmacological activity. And then you identify one specific molecule that has that behavior, and you identify what's called a conceptual framework for that. Now with machine learning, what you do is that you use computers. It could be quantum computer or whatever. You use computers to try to represent the action you are observing without actually manufacturing the real molecules. So you compute, and then, but it's like what is called it's a type of practical work, but it's practical work done by the computers. This is machine learning. And then you are teaching the machine. Now, the answer machine learning gives to you is not necessarily the same you will get from fundamental physics. Because machine learning is behind there is a mathematical algorithm that predicts. It's like you want to predict the height of kids your age with blue shirts and then red shirts. So, is there any correlation between these two things? In principle, no. But it could be that there is some correlation. And then you discover that using machine learning. Does it have to do with physics? Nope. It has to do with the model you use. Okay. So yeah, but that would be, you will have to invite me some other day to talk about that, because that takes some more time.
Okay. Well, thank you so much, Dr.
You have to invite me to one of these. But you didn't ask me what I like about this.
Oh my gosh. Well, yeah. That was terrible.
So she says, I like this and that this guy, our DJ.
So what is the best?
He's not playing music here, but he's
so he, I knew he was gonna make fun of any of us, or both of us combined at the same time. So can you tell us what was your best 2 or 3 topics that we talked today?
No, it's only one topic. I love the possibility of talking about science to young people. Because that's a way to explain what we do in terms that you can understand. And then you can go and explain it to your grandmother or your grandfather.
Yeah. So you can. I think a lot of kids need to start to get invested in quantum mechanics, because
from an early age.
Yeah.
Yes.
Yeah, maybe
absolutely.
something that you want to explore more. Yeah.
Hmm.
Yeah, we're here, and then we came back and maybe one of the classes in your Bible.
So how do we call this?
Futuristic
Futuristic
Friday.
Friday.
So here it is.
Futuristic
Today
Friday.
is Friday for Futuristic Friday,
But
its second episode.
Yeah.
Right. But it could be also be futuristic Mondays or Tuesdays.
Ooh.
Futuristic. It could be futuristic
day.
all week. We have parallel words. So who knows? We have other days than they're not in another planet. We will have more days.
Yeah.
What would be a name of a day in non-Earth planet?
Right.
There are 7 days on Earth, for the week. So how would be in another planet? I don't know. 8 days. I don't know. Did you stay quiet?
Yeah, because it could be. I mean, if you're talking about futuristic, then in principle, when you're talking about the future,
We're living
it
another
means-
planet.
It means that you are somehow you have the machinery to talk about the future. Because otherwise, imagine that you are in the Middle Ages and they ask you, which future do you want to talk about? And then at best, it will be tomorrow. So we wake up and then the tiger is trying to hunt us down. That's it. End of the story. Perhaps, as evolution took over, then people could start talking about a week ahead. And then people discovered at some point that they all were going to die. So then start talking about the time of death. And this was the future. But now we have a much richer version of future. You have all these things. And then you can ask, let's talk about a future where robots replace us. Because we think that we use them. But in principle, the use of artificial intelligence is the first technology in all of mankind history that can replace you completely. So that's very interesting.
Yeah, that could be the topic of the next time. Yeah. What do you think? Or we're going to talk about now? Yeah.
No, we keep it for next.
Yeah.
But then,
No, I don't think we have enough
next,
time to do
next I want some more pizza and some more.
Yeah. And DJ, come in the camera. You're hiding.
that.
And DJ has to actually be a DJ.
Yeah.
Yeah. I got some music in the background. I always like my mouth drop every time I talk to Dr. Mujica. Besides, he's making fun of us because that is part of what he does. And I call him, and he, out of the 2 minutes, 1 minute, he's making fun of me somehow. And then so he had to get some of that part. So DJ, he's gonna get
You
some.
see, DJ, I'm keeping quiet.
So this is so inspiring. So having somebody so knowledgeable, and then but you didn't get there just happen. He said pay the price to get to that point. Can you say what was the pay the price?
Well, I mean, the trying to get what some writers call a man of knowledge.
Oh.
So if it is scientific knowledge, you have to study. I mean, you want to be a university professor, you need to get a PhD, you need to be a postdoc, whatever. That's the usual path. There are some other paths. But that's scientific knowledge. If you are going beyond that and you are talking about human knowledge in general, that's another thing. So you have to study, you have to read, you have to think, you have to meditate, everything. So that's the price. So it's probably price is not the right word for that.
So it actually we had to enjoy that.
Oh yeah,
It had to be so enjoyment to that, gaining that knowledge. I had some, sort but no, I do appreciate always, as over here, but all the knowledge when I was his student. So maybe it could be the topic. What do you think could be the topic of our next podcast? Something that you brought up.
We already mentioned that.
The artificial intelligence. Are they going to take over the world? Maybe that one. Yeah. So
we can talk about that.
Ooh,
yeah,
that'd be very
artificial
interesting.
intelligence taking over the world. So yeah, so that would be for the next podcast. So stay tuned for the next Friday for Futuristic Friday podcast number 3. Yeah.